Okay, in this video we're going to continue our demonstrations uh, concerning three-level, multi-level models following from really the presentation that was presented in Chapter 4 from Heck et al.'s book on multi-level and longitudinal modeling with IBM SPSS. In the previous video we sort of exhausted the examples, but I thought I would kind of extend things just a little bit by incorporating the possibility that a level 1 predictor might, the slope for that predictor might vary between level 3 units, and then also looking at modeling a cross-level interaction between a level 3 predictor and a level 1 predictor. So in the previous video we had basically laid out the following specification where in terms of our fixed effects we had a level 1 predictor of math achievement, student level math achievement. So we had this variable right here, low SES, coded 0 for non-low SES student, 1 being low SES student. We had this variable right here, which was reflecting the proportion of students within a classroom who were identified as being low in SES. We had another level 2 predictor right here, which is reflecting teacher effectiveness. So that's a classroom level predictor. Then we had this predictor right here, which was reflecting the proportion of students within a given school identified as low in SES. And then we also had a composite of the teacher effectiveness variable associated with each school. So we had incorporated all those as predictors, and then we had also incorporated an interaction between the level 2 predictors, basically teacher effectiveness, and the classroom low SES variables. So we had also incorporated under random, we had essentially teacher effectiveness, the slope for that predictor varying between schools. And we had also incorporated a covariance type which was unstructured, allowing the intercepts associated with the classrooms to covary with the slopes for teacher effectiveness. So in this case, what we're going to do is we're going to look at adding in looking at variation in slopes for the level 1 predictor between schools. So to do this, we stay under the combinations for, and we have the school code identifier right here. And so we can move this predictor over to the add box. And right now we're just going to model this slope as varying between schools. So we're going to click on continue and on OK. And so now you can see that we have 15 parameters in the model. Really nothing else is going to be that much different from the previous model that we ran in the last video. But you'll see down here under estimates of covariance parameters, you'll see you've got the unstructured matrix for the covariance parameters. You see that the 1, 1 is reflecting well, actually, you'll see you've got the level 1 residuals right here. Down here, you'll see that we've got the level 2 intercepts, so reflecting variation in math achievement between classrooms. And then down here, you've got basically the variation in different parameters between schools. So the 1, 1 is reflecting variation in the school level intercepts. The 2, 2 is reflecting variation associated with the slope for the teacher effectiveness variable at level 2. And then we've got the 3, 3, which is reflecting the variation in the slopes for the low SES variable, that's the level 1 variable between the schools. So we're modeling that as well. The 2, 1 is reflecting the covariation between the intercepts, the school level intercepts, and the school level slopes for the teacher effectiveness variable. That's the covariance. Then you've got essentially additional covariances between this right here would be the level 1 slope varying between schools. and its covariation with the level 3 intercept, and then you also got covariation between the level the slopes for the teacher effectiveness and the level 1 predictor low SES, those operating at level 3. So you can see things get really, really complicated really, really fast. So this is the level 3 right here. And you will see, though, that the variation in the slopes for the low SES variable, we see that that is actually statistically significant. Meaning that essentially the low SES variable appears to exist, the slope for that variable appears to vary between schools. So we might then choose to add in a level 3 predictor of that variation. And so then we're talking about a cross-level interaction. So to accomplish this, what we'll do is we'll go to Analyze, Mixed Models, and Linear. Click on Continue, and then under Random, we're going to leave this exactly the same as it was before. But now what we'll do is we'll click on Fixed, and we'll add in now the cross-level interaction. So I'm going to leave it under Build Nested Terms. And then what I'm going to do is I'm going to use the school level low SES predictor as a predictor of variation in the slopes for the low SES variable between schools. So I'm going to add this predictor right here and then say by, and then the low SES variable from level 1 as a predictor, and click on Add. So you'll see that this is basically reflecting that the previous video, the interaction within level 2 between teacher effectiveness and classroom low SES variables. This is basically a cross-level interaction between the level 3 predictor reflecting proportion of students within a school who are identified as low in SES, and the level 1 predictor, which is the student level identifier for being low in SES. So now when I click on Continue and then on OK, you'll see that now we're up to 16 parameters in the model. And when we scroll down, you'll notice that we have our, basically these coefficients right here. A lot of these are very similar. So you can see that we have significant negative predictive relationship between the low SES variable and math achievement. Again, based on the scoring, where 0 reflects a non-low SES student. You can see the negative coefficient means that students who were who were identified as low in SES tended to perform worse in math. That coefficient was significant. The proportion at the class level in terms of identified as low in SES was negatively predictive, and that was significant. The teacher effectiveness variable, as before, was significantly positively and significantly predictive of math achievement. The school level proportion of low SES was significant predictor. The teacher effectiveness aggregated at the school level was significant positive predictor. This was the interaction between the level 2 predictors, and it was kind of near significant, I guess you could say. And then this is the cross-level interaction. This is basically the level 3 predictor, which was the proportion of students identified as low in SES within a school, multiplied by the level 1 predictor, the low SES variable. And we actually see that this was statistically significant in the model. And, really, without getting too far into the weeds, basically what we are finding is that that students who were identified as low in SES, their performance tended to be less poor in terms of math achievement in schools that had a lower proportion of low SES students. So basically, low SES, the relationship between low SES and math achievement was the negative relationship became more negative in schools with a higher proportion of low SES students, and the slope for that negative relationship actually weakens, and it's essentially less strong in schools with a lower proportion of low SES students.